We are carbon centric, period. This is a carbon world.
Hello, hello. So we welcome you to part 2 of this recording with Dr. Ramani Narayan.
50 years is 100 years. It doesn't matter. It's going to be a very long time.
We've heard this term time and again, polymerization.
It is the polymer molecule that is used to make the plastic, which is the problem today.
An inspiration of mine is a water spider.
The end of life has nothing to do with the beginning of life.
So in order to have the best cost economics, I'm going to buy the largest single line.
Natural polymers don't make good materials.
You've opened the Pandora's box now.
But that paper is coated in a plastic, and then you say this is paper product. That is disingenuous.
Extrusion coating happens all over the place. Smaller extruders can do it.
For them, biodegradability doesn't have to be 100% biodegradable.
In a temperature like India, it actually literally starts composting on the shelf at some point.
End of life must dominate the design of polymers.
Each time I speak to you, I'm definitely a more educated person.
You don't want to change the beginning of it. You don't want to change the end of it.
What does good garbage mean to you?
It's a very intriguing word is all I could say.
Hello, hello. Welcome to the Good Garbage Podcast. My name is Ved Krishna. My primary reason for existence has been to find ways to leave our wonderful planet cleaner. We will be speaking with material innovators, creators, and propagators to learn from them how we can build for scale and towards a regenerative future. Their stories will help us answer the big question, what is good garbage? Hello, hello. So we welcome you to part 2 of this recording with Dr. Ramani Narayan. We've had a rollicking first section and conversations on the wide idea of polymers and things like that. And now, of course, we are ready to dive into what we would call the meat and potatoes of the conversation. Let's get into it, Dr. Narayan. Are you ready?
Sure. Let's go for it.
Okay, so PLA. What is the story with PLA? What the little kind of that I know that the material existed for a while, but then you decided that this could be a great packaging material. So take us into the history of this idea of polylactic acid, and then how did you get into this this thought that okay, let's make it into a packaging substrate?
Okay. Well, it is an interesting story. You are correct. PLA, polylactic acid, is not a new polymer. It has been around since the 50s and 60s. Carruthers, the famous scientist from DuPont, invented that, and it has become a medical use product for ages. I mean, go back to your sutures, your delivery systems, scaffolds, and even in stents, heart stents. So it always intrigues me, or I kind of smile at it when people question, is PLA in the environment a problem or not? Well, if you're able to put it into your body and use it efficiently and effectively, the environment can handle it. Okay. So, but that's just a anecdotal connection, and there's no science behind it. But it begs the question: this is not something like a problematic, you know, chemical that's the problem. It has been used a lot in the human body. So let's put that aside. The requirements of biodegradability in different environments is something which PLA is needs to respond to, which is in the body. What happens is after use, the PLA does it should not cause any immune responses. B, it should survive for the time in which it is used. It can't go into the body and then immediately disappear. It has to deliver the drug, or if it is used as a scaffold for bone growth or similar applications, then it has to survive that time, and then slowly it is going to break down and be removed from the body and absorbed by the body. So, which is where the advantage of a biodegradable scaffold or a biodegradable stent comes into play. If you put in a metal stent or a metal scaffold, then you have to operate again to take it out. It's not going to go away. So that is the beauty and value for the biodegradable materials in biomedical use in the human body, so to speak. And therein lies the problem in the environment, because if you look at the human body, A, it should not cause immunological responses, but B, when it breaks down, the breakdown products of PLA must be absorbed or reabsorbed by the body, right? I mean, it has to be complete, can't go anywhere, so it has to be reabsorbed by the body. But what remains, the polymer or oligomer or whatever remains, is excreted from the body. So there is a mechanism in the body to excrete what is not broken down and reabsorbed by the body from the body. Okay, so that's how the biodegradability works. Does it form? These are small molecules easily absorbed and cause no immunological responses. It is safe. It works during use, and then you can easily excrete it from the body. So for them, biodegradability doesn't have to be 100% biodegradable. And therein lies the problem when we consider the biomedical scientists questioning what is going on. PLA has been approved as a biodegradable polymer. What's the problem with the environment? The problem is pretty straightforward. There is no other place to excrete from the environment. It stays in the environment. And therefore, what happens for the released products in the environment is got to be addressed. So does it have an impact? Does it have microplastics? Is it got things which is going to impact the local environment, right? So this has always been a point of confusion and misperception is a better word to describe this. In the human body, PLA doesn't have to biodegrade completely. The biomedical scientists do not look for CO2 as the endpoint. They simply want to establish that it does not cause any immunological responses, cause any negative effects. The breakdown products, lactic acid and anything else which goes with it, glycolic acid, they are all copolymers used within the biomedical environment that they can be resorbed by, they call it, by the body. And whatever remains of the polymer can be excreted from the body. But this does not happen in the case for the environment. So there is a fundamental difference in PLA. So I wanted to preface what we talk about PLA to make sure we are very clear that we're not talking about PLA in the biomedical usage and the methodology and protocols and the approvals and the standards associated with that versus what we're talking of the environment. It's pretty straightforward. It is the environment doesn't have anything else to excrete to, so we need to respond to that. So that is about PLA. And that leads to a question like we talked earlier. PLA has been around since a long time. Boehringer Ingelheim is one of the companies, they're still around, making biomedical grade PLA. And PLA copolymers, lactide, glycolide, there are medical companies which use it. I'm sure in India, worldwide, it is used. And the question was that the amount of biomedical usage is in maybe 1,000 pounds or so for the whole world, literally. And so you could not worry about the economics, the cost. So PLA was $1,000 in this when 60s and 70s when they were using it, a kilogram. But when your health is an issue, when you're talking about heart stents, price is not the problem. And so the amount is not the problem. So they could use the process, which is not necessarily the best chemical engineering approach to making it, but to make it so that it is pure, and you can therefore and process it in whatever shape or form. But say 1,000, I just use an arbitrary number, but thousands and several thousands of dollars per kilogram is what PLA used to cost in the biomedical field. Now, so that's sort of the history of PLA and why it did not become a commodity. And your question was, why are we not using it as a commodity? It's fundamentally this: there's no way $1,000 a kilogram uh, would be acceptable. So that's where it stood till Cargill came along. Cargill is the largest world's privately held agribusiness, as many of you know. They call themselves the supermarket to the world for everything. And their management felt that they needed to come up with, they wanted to enter the field of environmental products. But more than that, the company felt that they needed to create a legacy polymer, something which is very different. It was not economics. It was not our mainstream. Can I sell it today or tomorrow? And at that time, Cargill management, that is their corn wet milling business, came to MSU, Michigan State University, with a proposition: what do you have in the fermentation based space that is a that can produce a polymer that they can uh, commercialize? And they wanted to call it a legacy polymer. And since this is a podcast, I can share some of these discussions which has not science associated with it, and to tell you how PLA became today based on something which had nothing to do with science, right? So Cargill wanted a legacy polymer, and the the general manager of the corn wet milling business is a gentleman by the name of Ernie Misek. I don't even know if people know about it, who then became chairman of Cargill and who I is since retired. I don't think he is anymore at Cargill. This is 100% Cargill business. And so when Cargill came to MSU, they wanted a legacy polymer. And the criteria was very simple. It has to be fermentation based. And you may ask the question, why fermentation based? Because um, Cargill and many of the agri businesses are very strong in fermentation. They make ethanol. They make other sorts of nutraceuticals and other things they can make. So fermentation, scale up fermentation, is um, something they are comfortable with. They have the engineers to do it. And that's how they decided they wanted to get into a fermentation based polymer that can be used globally and can be that legacy polymer to leave to the world, so to speak. And so with that, there were multiple. We can make polyesters, PBAT, PBS, we talked about it. All of that they could get into. And the anecdote is there's also starch based. You started your podcast with saying, look, there are these starch based polymers. And you said, why are we not using it, what it is? At that time, I was working with starch polymers, starch copolymers, and saying, hey, starch is inexpensive. Cornstarch is 10 cents a pound. We will modify it. We'll make polymers out of it. But Cargill was not interested in that. They wanted a legacy polymer that the entry to that business, and you as a businessman can appreciate this, is so high that not any Tom, Dick, and Harry company can just come in and start that process. And it means then that we wanted the entire process, and we want the cost of to entry for anybody else to be very high. Now, this is my read on it. Why would they not do starch? Because I asked the question, right? I got all these products. Why don't you use it? Says, no, that's not our interest, and that's not what we want to do short term. Or the idea was not to make money; it was to create a legacy polymer that will always have the Cargill name associated with it. And today I can tell you that that's true. They started it. So that's the story around how Cargill decided to get into the PLA business, because the feedstock to make PLA was lactic acid, which is produced by fermentation. For that fermentation process, they had exceptional engineers to build it. They had built plants around fermentation technology. So what was missing was the polymerization part of it. And so that's one. The second interesting business tip, we are not talking business here, but this is the business thing. This is not a one step, this is not a polymerization process, this is not a separations process, this is not just a fermentation process, it's all of the above. And it has to be integrated. It is not that lactic acid, which is a commodity, not a commodity, a food grade ingredient, has been produced by many companies. Not many, but a few companies selling lactic acid, but they never polymerized it. The people who made the PLA for biomedical use did it in a way in which was not economically feasible to scale up. And that's where the beauty of chemical engineering comes to play, which said that if you integrate all unit operations with a transfer at site, you can make a polymer that will be low cost. And the goal at that time was to make it around $1 a pound. You say, was no fancy economics done, and just it was a number pulled out of the air and said, we want to make this. And Cargill felt they can do it because they are used to fermentation at scale. The polymerization they thought can be built in. And they were willing to invest in a legacy polymer where nobody else could get into it. So you can see today the world is now getting more PLA plants. But between the time when Cargill NatureWorks built their 150 kiloton PLA plant to today, there's a huge gap. That's because the price to entry was very, very large. And I never did an MBA, but I learned all about business issues and business points from observations and discussions of why some companies did that. So that's why Cargill got into it. It's just the background to what on the world is Cargill, an agri-business doing with a polymer called PLA for plastics, right? That was the story behind why PLA was selected. The other interesting thing is chemical engineers operate by what we call as unit operation. So not unit operation, but scale. So you'd build a lab scale, then a pilot scale, then scale, and then you go up. That's sort of the typical way scaling is done. This is my take on it. I felt that Cargill did not, or many of the agribusiness, even ADM, I think, don't believe in this scale approach. If it works, let's build at scale, and then we will sort it out. Anyway, if you're convinced of your technology and it works, we'll build it at scale. After all, what is the difference between doing that pilot and all? You're simply qualifying whether it can be scaled or not. When the company has made the decision that they are going to make this and it is technically feasible, then why hop around doing small and all if money is not a holdup, right? So Cargill went directly from a small scale to a 10,000 pound pilot and then straight to the 150 kiloton plant, which is not the typical norm of a chemical industry. In fact, some of the other chemical companies asked me, this is crazy. Why are they doing that? That's how agribusinesses operate. And with you being in that sector, know that that's typically the agribusinesses operate, that they don't operate at scale and slowly move up. So that's how Cargill got into the PLA, because they felt that that was a legacy polymer. They could leave their imprint. They had the foundational engineering expertise, and then they could put it all together. So I thought I
Yes.
was here to just let
No, no.
you
Yeah.
digest
Thank
this
you.
information on PLA.
No, thank you for sharing. In fact, yesterday, talking about agribusiness, yesterday I was talking to somebody who wanted us to set up a bagasse-based unit in another country. And I told him, do you have 500,000 tons of bagasse? So he said, I have 300,000. Why do you need 500,000? I said, see, a single line right now, a proven single line can process 500,000 tons in a year. So in order to have the best cost economics, I'm going to buy the largest single line. So the pulp is the central aspect in our case.
Yes.
So you don't want to compromise on that. Like whatever it can process in a single line, that's what I'll do. Forward and backwards, we can figure it out. So that became the kind of, yeah, I understand the idea of maximizing the potential. But let me take a step back just to understand this idea of PLA more. So you said it was being used by medical devices. So when we look at the structural differences, and you said something called polymerization, which I would love to learn more about it. We hear a lot about it, but it'll be interesting to know more about it. But keeping my questions separate, what was the raw materials used when they were creating the lactic acid based sutures and other things? And then was there a shift that you did in terms of the material that you created for polymerization? Or was it the same material and you polymerized it and you created something which was not conceived at
Right.
that point?
Lactic acid was already on the marketplace, right? It's used in food and other grades. So if you want to produce 1 kg, 2 kgs of PLA, you just purchase the lactic acid. So the companies were set up around not to make lactic acid, but to take the purest lactic acid, make the polymer in a small scale, uh, for biomedical usage. But it has to be absolutely pure. It must meet all the regulations and all. So there, the issue was purity and not cost. For a scaled approach, your example of pulp is perfect to this. For a agribusiness to operate, they need to utilize their feedstock, which is corn, and the cost of sugar from corn, right? How do you make sugar? Because lactic acid is produced by fermentation of sugar. I'm using generic term sugar, which is needed to do the fermentation and processes. That sugar can come from a number of sources. Any carbohydrate feedstock can give sugar. So, bagasse, sugar cane. So you note that it is not to me, it is not surprising that in India, it is the sugar companies which got into PLA, and my analysis, I won't put it on them, but it makes sense to me, is the same reason why Cargill got into it. You had sugar, you are competing in the open market on sugar costs. Can I create a value added product out of sugar? It wasn't not PLA. It was, can I make a value added product of sugar which has got a good application, a good end market use? It's a no brainer that companies which are in the sugar business, whether it is the companies now or who have access to bagasse, lignocellulosic residues, or corn. In the US, it is corn. And the the economics works on how inexpensive you can make lactic acid. So you need feedstock that is inexpensive at scale. So, not anybody can make a bagasse pulp paper plant by taking 10,000 pounds and say, I'm going to build a paper plant. Economics won't let you. That's why you said in your uh, earlier talk, was it just now when we were talking, I need 500,000 pounds to put one line. Without it, the economics don't work. Same principle here. I need to have a sugar base which will be large enough at low cost to make lactic acid and integrate it all the way to PLA. Then the economics work. and that is what Cargill did. So the first plant, if you look at, was built in Nebraska, U.S. Nebraska is the largest corn growing state, producing a lot of corn. Then, we are in Michigan, and you would have expected that since all the work was done in Michigan at MSU and at MBI, which is located here, they went ahead and built it in Nebraska because even Michigan's supply of corn was not big enough for that integrated plant. So that's why it went to Nebraska, which may have caused a few heartburns here, but it was the logical decision to make to go there. And it's still operating because the amount of feedstock availability was there. And they could sign, like in business, long-term contracts with farmers. They're not subject to price fluctuations. Oil is today $80, tomorrow it is $100, then it comes, whatever happens in that part of the world, suddenly it changes. They're not subject to any of the fluctuation. So from a business perspective, it made sense for the country, which is in this case the US, to use a feedstock that is in surplus. The US is the largest producer of corn, the lowest cost producer of corn. So when people talk about environment, and I know in some of your podcasts you question, isn't corn a feed? Is this corn about food? And what that question has been raised. But corn is not a food product, it's a feed, it's an animal feed. And we produce more corn than they know what to do with, right? And this is the reality of it. And so it made perfect sense that you want to use corn as the feedstock, especially in the US. In India, where you have sugar cane and where there are sugar mills which are producing large quantities of it, it makes sense for you to look at another value-added product. And the biochemical lactic acid and PLA made sense. So if you really look at it from pure business sense, take the word environment out of it, it makes perfect business sense for some of these sugar companies, which including pulp and paper companies like you are, to look at, can I take the feedstock and make sugar which can go into PLA? You're better off making PLA, which is a more value-added product, than making sugar and selling it in the commodity open market. It creates value for you. And that's a very simple proposition, right? So that's how that the purchase, the tying it into the feedstock comes into play. Corn. Thailand, the same reasons why it was located, for two reasons. One, the availability of feedstock, but also the governmental support for it. Huge governmental support. Thailand wanted to become the world's largest bioplastics manufacturer, which they are today. They have 2 PLA plants in a small country of Thailand.
Interjecting here, so staying with lactic acid. So you said it's all about economics. So once it's lactic acid, and this is a presumption, so please correct me if I'm wrong. So once it's a lactic acid, it doesn't matter where the feedstock came from till it's a certain purity of lactic acid. In terms of all the available sugars, what is the most economical, according to you? Does the US cornstarch work better than a Thai sugar juice? So is there an economic understanding of that this will create the lowest priced lactic acid? And then, of course, please address my my presumption if it's incorrect.
No. So it doesn't matter which is the feedstock which produces lactic acid, as long as it's got a purity required for polymerization, right? I mean, that's given. You asked the question, which feedstock is good for producing lactic acid, or for that matter, producing any biochemical product. And this is where we collide, at least I collide with some environmental claims which says first generation feedstock, second generation feedstock, third generation. We really should get away from first generation. And my thing is, there is no first and second and third. This is the whole idea of agriculture. It grows it every year. So where is the second generation? And we'll talk about that in a minute. But it is country specific, Wade, as to what feedstock would make most sense. It is not one giving you everything. So in the US, it will always be corn. There is no way any company can come into the US and say, I'm going to make PLA from waste, or I'm going to make PLA from lignocellulosic material because it's good for the environment, or I'm going to grow specialty crops which will give me PLA, right? Feedstock wise, because you cannot produce sugar at a price point cheaper than what corn can give you. Just the volumes tell you that. It's good academic discussion, which crop is better, and can I use Jactropa, or can I use this, can I do that? But it's a non-issue from an economic perspective. So in Thailand, obviously that accessibility to sugarcane, bagasse, and thing made that as their value. India, of course, multiple choices are there, which makes India a very uh, nice alternate to produce PLA. In fact, wondered why PLA has not gotten into production, given all the feedstocks, agri feedstocks available to make lactic acid.
And then, of course, you'll have a certain price of lactic acid depending on where you are, what was the cost of your feedstock, what was the recovery rate, and ultimately, what was the purity of the lactic acid itself. So,
Yeah.
parking that part of the discussion, we've heard this term time and again, polymerization. So, and of course, polymerization seems to happen with all sorts of things. So with you in the house today, so I want to dumb it down. I want to ask you, what is polymerization? Can it just happen with any material? What does it take for a material to be polymerized? And then what are the properties that you're seeking from once it's polymerized?
Okay, you opened a big space to talk about. So let's make it simple. A polymer molecule, which has got value, a polymer, is nothing but a long carbon chain. Doesn't have to be carbon, but majority we are talking about carbon long chain polymer. It is like putting beads together to form a necklace, right? And so you form these long polymer chains, and the entire science and engineering around polymer science, polymer chemistry, polymer physics, polymer engineering has evolved around it. Okay, so these are long chain carbon molecules connected to each other, and they may have other groups. They can entangle, you can cross link, all those chemistries get into play. It's a very simplistic polymer explanation. What many do not understand, this ties into the word of the use plastics. So today, plastics is dominated by these carbon backbone long chains. 76% of all polymers used, all, okay, we have is based on these carbon backbone polymers. And you wonder, how can you do that? That's the beauty of the polymerization process, that by changing a group attached to the backbone, and I won't go into the details of the polymerization itself, the chemistry of it, polymer people will understand it, this building of this carbon backbone with different properties to give you polyethylene, polypropylene, polyvinyl chloride, polystyrene, is based on changing that group attached to the backbone polymer in a very simplistic way. And the polymerization process, which is called the free radical polymerization process, to make these is more or less follows that same pathway, the steps involved to make that polymer. Okay, so uh, that's what pushed forward this whole area of uh, making polymers from carbon-carbon backbones. Now, nobody uses this word because nobody understands it. You talk plastics. So what is plastics then? Traditionally, plastics is a property, plasticity. It is simply asking the question, if I heat it, it flows. And when I cool it, it takes the shape imposed on it. And so the processing becomes very simple. A lot of products, articles can be made, whether it is injection molded, whether you make it into a film, whether you thermoform it. All these downstream processes is based on a fundamental principle that the polymers that can be processed are those which can, they're called thermoplastics. That's the correct terminology. The thermo is dropped and we are left with the plastics tray. So thermoplastic simply means that you apply heat, that polymer melts or can flow with high viscosities, but flow. And so you can throw it into a cavity of an article, you can blow it like a balloon into a film, you can pull it, all sorts of downstream processing. And that ties beautifully with the thermoplastic polymer. Okay, so there's two steps. One is the polymer resin, which is the word used, resin, which is making these carbon-carbon polymers, the polyethylene, polypropylene, polystyrene, which dominates the plastics industry. So the issues involved with plastics has got to do not with plastics per se. Remember, plastics means you can heat it, it flows, I can make any sort of articles. That's the most energy efficient process. Very lightweight. So all of the good properties you hear about plastic, strong, lightweight, efficient production, great barrier properties, performance metrics are huge. That fits in perfectly with the plastic. And so the real question which should have been asked, which we don't ask, is it is not plastics or the plasticity or the use of plasticity to make products the problem. It is the polymer molecule that is used to make the plastic, which is the problem today. In the case of plastic, 70% comes from this carbon-carbon backbone. There's another number I would like to introduce. 90% plus of packaging is carbon-carbon backbone polymers. You look at all sorts of packaging, they are based on the same, whether it is polyethylene, your milk jug. You talked last time we talked about a milk pouch, a film, polyethylene. I mean, why did that take over glass bottles? I mean, just imagine the weight of a glass bottle carrying the same volume of milk versus a pouch carrying the same volume of milk. There's no comparison, you know. And so clearly the plastics processes win out on this. The plastics wins out on it. And because it has become so dominant, we associate plastics with the polyethylenes, the carbon-carbon backbone polymers, to put it in a nutshell. Okay. And that I don't think a Professor Narayan is ever going to change. That's a perception which has now become reality, that plastics is associated with those carbon-carbon backbone polymers. So, and because they form microplastics, obviously, because that carbon-carbon backbone has been designed to not break down, to be strong, which is why you use it in the first place. Now you want that when it leaks into the environment, or you just throw it away, then that creates problems, right? Microplastics, microparticles, if there is rains, it clogs up things. All of those issues is what happens when it is end of life comes into play. You have to either intervene to recover and recycle, which is why you see this push towards recycling, or you make it biodegradable, because you can then put it into an industrial composting environment and you close the carbon loop around it. So that's really why it is. So I hope I explained to you why this problem has arisen, and it is the backbone part of it. And it is that which has spewed this, what I call the false industry of adding additives to carbon-carbon polymers, that it will break it down and will biodegrade. Because you don't want to change the beginning of it, you don't want to change the end of it, because they are so perfect, right? It's all the downstream processes, which is, I told you several of them: injection molding, thermoforming, films, flexible film, all of that is based on this fundamental property of plastic, right? And a country's economy, in fact, I have a little more understanding of what's the economics in India. These downstream processors contribute significantly to the GDP of the country. So you can't simply ban all the plastics and then what will happen to these processors? So they need to have a different material, different polymer molecule to do that. And that's not been discussed. I mean, I don't think it's in your podcast. It's not in the discussions there, that the ability to take a polymer, buy it from the big producers and make articles, whether it is for agricultural utility articles or a textiles to create different, to point out the hangers, other things, lots of products, right? But they are all produced by processors who have a business in that, provided you give them a polymer molecule that they can process with their equipment, which is basically that it must flow when they heat it up, and when you cool it, it will take the shape imposed on it. That's the fundamental property of plasticity, which uh, I have this English saying, don't throw the baby with the bathwater out. That's what my worry is, that don't throw the whole thing out because you have a problem with the end of life.
Okay, you've opened the Pandora's box now on the other side. So I have 100 questions on that. So let's stay with the first bit, and I'll sequence it so that it's easier. Again, staying with polymerization. So when you see a petroleum process, a distillation, you'll get a bunch of gases, is what I'm told. The ethylenes
Monomers,
and
yeah,
maybe the
yeah.
styrene. Yeah. In lactic acid, I presume it may be a liquid, and I'm presuming again. So how does one take that gas or the liquid, and ultimately what the processor gets is a granule? So, and I presume that's the process of polymerization.
Yes,
So
correct.
how does the gas or the liquid become a granule that is so homogeneous that it can flow into, like you talked about thermoplasticity?
Yeah.
It once heated, it can be kind of extruded into a different
Product,
structure,
yeah.
and then films and all of that. So what is that process that enables a gas or a liquid to be made into a granule that is thermoplastic?
This goes back to the refinery, the chemical refinery, right? Your feedstock is uh, naphtha, and you in India does the same, as does the US, the big refineries. And the feedstock is naphtha, or the feedstock is natural gas. This is the feedstock. So carbon feedstock. Now, uh, agricultural feedstocks can they be used? It's got a lot of oxygen, which messes it up in the refinery. Keep that in mind as to why the naphtha and all. So this chemical refinery, in a very simplistic things, takes naphtha, takes natural gas, and converts it to a series of uh, molecules, ethylene, propylene, styrene, and certain processes around it to create the starting materials to make polymers. Now, the interesting business of refinery and making these polymers and plastics is that the major um, revenues coming from a refinery is fuel, transportation fuel. Almost, I wouldn't, my numbers may not be totally accurate, but uh, if I remember, 80% of the revenues of a refinery is in the transportation fuels area. The 20% is in the polymers area, not revenues, the uh, amount of materials going into those two areas. But from a revenue perspective, that small chemicals to polymers plant gives you much more than what the transportation would give you. Something for, I have the numbers and maybe at some point we can share it, but I don't can get off the top of my head tell you exactly. But it's certainly there. So without these polymer, uh, monomer polymer contributions to a refinery, the economics doesn't look good. You cannot make the economics around pure transportation, right? By the same token, you probably cannot make the economics just around the polymer itself. Then the scale, we talked about scale being an important, the scale will have to drop to small numbers, which may not make, nobody has done the economics, but these questions have been asked and raised. And I know the big petrochemical companies uh, must be going back and forth on what is that scale where uh, the amount of transportation fuels is going to go down, electric vehicles, for example, right? Such that the chemicals can sort of do that. That is where the refinery, can a refinery ever be, uh, downstaged to smaller? Those are not answers which we know of, but that's where the situation. So to specifically address your question, the types, because you're using, uh, we make it very simplistic, right? Fossil fuel versus bio feedstock. Well, what is so different about the two? The fossil is also made from the same carbon cycle. It didn't come from somewhere else. So that fundamental difference is this fossil feedstocks, naphtha and natural gas, are basically carbon hydrogen molecules, very little oxygen. The biomass, which is the precursor to making, to nature forming coal and oil and all that, has got a lot of oxygen. So you are going from a highly oxygenated material to a very rich hydrocarbon material, which functions as fuel and which can do this. So the debate about fossil versus biomass or feedstock is presented in terms of the environment. One has to be very careful. They are both around the same carbon cycle. So it is not which is better. It's the question is the end of life for that. And the environmental impacts of, say, fossil versus biomass feedstock refining. That is where that comes into play. So the polymers of today are all hydrocarbon plastics. You take all the polymer molecules used today, the carbon backbone I talk about is the hydrocarbon polymers. And they fit beautifully into a chemical refinery which processes naphtha or natural gas. And so that's where the equation is. So park that for a minute and say, if I want an end of life like biodegradability, industrial compostability, this will not work. And this is clouded by the claims of adding an additive. That's where this whole thing comes. If I don't change polyethylene, polypropylene, if I make a magic additive, it will biodegrade. So is polyethylene biodegradable or not? That's what we talked about for first podcast. Is it 50 years? Is 100 years? Doesn't matter. It's going to be a very long time. So for practical purposes, it's not biodegradable. I use the word practical. All right. So that's not going to change. That is thermodynamics. That is fundamental science. So what you can do is to change the polymer backbone. And that's where the PLAs and the PHAs and come into play. They are taking the molecules and creating ester backbones. So can I make these types of ester backbone molecules from fossil feedstocks? Absolutely. PET is a classic example. It's an ester backbone polymer. PBS, PBAT, all these biodegradable plastics in the marketplace is made from that same feedstock, but it fossil. But so we've talked earlier that the end of life has nothing to do with the beginning of life. You can do it. It's a question of economics and what works, what doesn't work, and the perception. I made it from natural polymers, right? This is the word used. Uh, uh, Polymers made from fossil are also natural in the sense. It's just that it was created over millions of years, and so we sometimes become superfluous with these words, natural, and I think we should stick to the science part of it, which makes life much easier. So to answer that fundamental question, the refineries, and we're building more refineries, because of the scale, the price points are very low. So you can buy the polyethylenes and polypropylenes, and because of the work done by so many scientists and engineers, its performance has continued to grow, such that you can make a steel a vest, an armor, what do you call it, protective vest from high density polyethylene molecules. The same which you use to make a milk pouch can be used to make a body vest, armor vest. I mean, that's how well the polymer science and engineering around it. But it's all based on that carbon backbone polymer, and nobody explains it that way. I have taken that to explain it because that's what that if you change that, you make esters, then yes, you can create biodegradable polymers, and it can be from fossil or it can be from plant biomass feedstocks. PLA and lactic acid lends itself better to the sugar, the agri-business type, and you can close the loop around it. Regenerative agriculture and all fit into that theme. So that's why you can talk about PLA as not belonging to that refinery. Not that they couldn't make it. Chemically, you could also make lactic acid in that refinery by switching some of it. But I don't see that happening, because why would you do that? You'll have to compete with now a lactic acid made at scale with these things. So that's not going to happen. What I'm trying to get at is that uh, it is because of the refineries that allow you to produce these monomers, starting molecules, that can be polymerized to a variety of products very easily and efficiently with high performance metrics associated with it, is what drives the whole use of plastic. But it is that same high performance metrics, its non-biodegradability, that when it leaks into the environment becomes its problem. So that's what we have to resolve in this.
So my base question, and maybe I'm not being able to like explain
Separate
the
it.
idea. So say if I look at a PHA plant. So once the microbes ferment and eat into whatever the feedstock is, what I've seen come out is like a powdery substance, and then they put it into something and make it into granules. And similarly, when I look at a lactic acid plant, maybe liquid, and then maybe I don't know if it becomes a
Yeah.
powder and then it becomes a granule. So one part of the question is that, like, what I was trying to understand is how does it take that granular form from a gas, from a liquid, from a solid? One is that. And the second part is intriguing that you mentioned that it doesn't have to be a carbon-carbon. It could be something else and it could be polymerized. So I don't know if it makes sense, please address it. If it doesn't, ignore it. And
No.
and
I
then we can
think
go on to.
and since you're asking the question, we need to explain it. The granule has nothing to do with the polymerization part of it. It is a downstream process where you can feed anything, a powder, uh, add color, add additives, and they call them compounders, right? And you can pelletize it, and you can form these nice granular pellets. The same applies for PLA. Once you take it, so because why do you want it in that nice granular pelletized form is because it's easy to process. They're all uniform, the regularity and all. And that going from powder or any form of product to that is based on that fundamental property of thermoplasticity. Right? That's what. So we do it even with starch, right? All your breakfast cereals, they're all nice, granular thing. And you use the same extrusion process. You add water in this case, you add starch, and you run it through this process, and then you chop it into whatever shape you want, and you give them cereals, right? The only difference between the two operations, the way I present it, is when you prepare breakfast cereals, you want it crunchy. You don't want it leathery and soft and that no taste. So the whole process is tuned to making it brittle, crunchy. Whereas when you want to make products to make into film and other things, you want it more flexible, more leathery. And so while the process unit may be the same, the way in which you do it changes dramatically for a plastics versus a cereal for food manufacturer. Not much difference between the two, right? But in terms of the units, it's how you process it and what is your starting material. So the granules which you're focused on is not an issue. It can be done with both, and whether it is in powder form or granule form is just a unit step to do that. That's not any differentiator between using a plant biomass versus using a petrochemical produced starting material.
Got it. No, thank you for explaining that so well. So again, coming to the second part of the question, you said it doesn't have to be a carbon-carbon change for the polymerization. It could be something else. So what does that statement mean?
Remember the first statement I made, 90% plus of all short life packaging materials are based on this carbon-carbon backbone, which, as we said, is very strong, lightweight. It's got all the best properties, but in the environment, it is going to persist, build up, and that's what you see all the stories on microplastics and all come up. And the debate around, isn't that the customer's problem? Isn't that the consumer's response? All of that debate centers around it. From a technical science person, I am saying, okay, if that is the problem, let's change it. Change the backbone so that it won't last that long, that it can break down, and microbes can then assimilate and utilize the broken fragments easily and in a practical time frame. And that this also should not lead to saying you can therefore throw it anywhere you want. You build the waste management infrastructures to handle that. And that's another debate. So do you build composting for plastics? No. Composting is needed to just manage, as we said in the earlier talk, to manage the 50 to 60% of biodegradable organic waste which exists in every country's municipal solid waste stream, which today is either dumped or put in a landfill, which makes no sense. That is what we are addressing. And so we're trying to redesign. So if you look at my talks, I always say redesign the carbon-carbon backbone polymers to ester backbones or similar linkages, which are not as strong, which can break down under hydrolytic conditions. But that breakdown must be such that the molecules created from the breakdown will be microbially utilized. So it's not one stage, it's a two-step thing. break down, and then microbially utilized. Therein lies all the what I call misleading things which evolve, which says, oh, I can give you something which will break it down, and then say eventually biodegrade. So this is where all the confusion is. And to your listeners, but to the whole audience, the key question which has to be answered by any polymer, whether it is based on ester backbone or carbon or anything, you must validate that 90% plus of that polymer carbon has been microbially metabolized as measured by the evolved CO2. These are, and there are ASTM ISO standard test methods and specifications for you to prove that. So all I am suggesting to the audience is trust but verify. If somebody comes to you with something, if it's too, there's the other proverb which says if it's too good to be true, then it's probably not true, right? So you want to make sure that you verify anything which is given to you as your end customer. That is important.
We would like to take a minute to thank our sponsors. Good Garbage is sponsored by Paka, a family of brands that produces compostable packaging and works to implement regenerative solutions. Paka's new project is to bring compostable food serviceware and food carry products to the North American marketplace. Learn more at Paka.com. Now back to the conversation.
So let me take a step back to nature. And obviously, there are enough polymers and more in nature. And there is synthetic chemistry happening, etc., etc. So now, if I look at, and that's what I was trying to derive when you said it doesn't have to be carbon. So when I look at the building blocks, it's either carbohydrates or amino acids. And what happens when an amino acid based product polymerizes? So an inspiration of mine is a water spider. So a water spider makes a web of amino acid based polymer that creates this beautiful structure that can breathe inside water. So that chain, I presume, is totally different. And then obviously linking it back to products. So should us humans be looking at a different structure altogether as well, which is maybe not a carbon oriented chain? Or does that also have basically carbon oriented with say amino acid based product which is polymerized?
We are carbon centric, period. This is a carbon world. Yes, there are silicons, for example, and there are Dow silicons is a classic example. Your lubricants is made out of a silicon backbone, SiO. But predominantly we are carbon centric. All the issues we are talking about is how do you manage carbon, right? That's really what we are talking about. How do you manage carbon? And nature manages carbon through the biological carbon cycle. They also have the nitrogen cycle and the water cycle, but go back, every high school kid has studied the biological carbon cycle. That you still want to keep that in mind. We're not going to go away from carbon. And this is an interesting play of words. You see these two words played out in the social media space: defossilization and you heard that word, and decarbonization. Totally different concepts, in the sense that when we talk about decarbonization, it's primarily related, not, I would say almost completely related to energy. That instead of using a carbon feedstock for energy, I use electricity, but the question can always be asked, where did that electricity come from? It must probably have come from a carbon. But decarbonization, reducing my carbon use. The materials world is really focused on defossilization. Reduce the use of fossil feedstocks and enhance the use of biomass plant feedstocks, which ties into agriculture and regenerative agriculture, right? So we are talking from in a materials world of defossilization, But in a broad sense of energy, they are talking decarbonization. And those two words get intermixed and confuses everybody. And it is not used properly. So carbon is still going to be the primary element that we are going to talk about when we are talking about materials. Whether you talk paper, whether you talk a fossil-based plastic, or you talked about the not synthetic, but proteins made by spider webs and all these things. They are also amino acids, but that backbone is still got carbon in it. It's a carbon. So the only difference is I use the word ester. The other terminology there, it is a polyamide. It's got a different linkage, which gives it more strength and gives you better properties. The spider spins it using proteins, and there are technologies people are trying to mimic it. But this is where then the economics starts to play. Those are all complex processes which you're trying to model and build on. It's not going to give you your commodity milk pouch, right? And the second part you said is these natural polymers, cellulose, starch, lignin, and there is even a group which says we need to focus on natural polymers. I'm not sure what that means because natural polymers don't make good materials. I mean, the paper industry has learned it very well, right? You add lots of stuff into the paper making process to give it strength, and then to give it moisture and grease resistant and all that, you coat it. You don't say, okay, I got a natural polymer and so use it. Now, people are saying this is a paper product, and I have no reflection on whether it's paper or plastic, but you can look to the advantages of one versus the other. But that paper is coated in a polyethylene coated plastic, and then you say this is paper product. That is disingenuous. You're saying, oh, I don't have plastic, I got paper. But you have hidden the plastic inside the paper and then you're selling it. That is disingenuous, and that is happening today. So how do you handle that? The Ved Krishnas of the world have to address this. How do you not make that happen? Because that is outright misleading and disingenuous.
So what happens to things like, what happens to things like collagens? And they are also carbon backbone?
Yeah,
collagens.
they're all carbon backbone polymers. Some are water soluble polymers. You talk about any of the proteins. When I say carbon backbone, there is carbon in the backbone because they have other groups. Like if I say it's ester backbone, I'm not saying there is no carbon, right? That ester has a carbon in it. When I say carbon backbone, there's nothing else. There's no oxygen. There may be some nitrogen, but nothing else in it. The proteins you're talking of has got carbon in the backbone, but it has also got oxygen and has got nitrogen. Now, how you put it together is where the performance and properties come, but they've still got carbon. 50%, 60% is carbon. If you simply burn it and say how much carbon is present, they all contain carbon. So you're not talking about when you say I'm using this new spider web protein molecule or amino acid molecule, you can't say there is no carbon in it. There is carbon. And that carbon has to go somewhere. So it has either to go into the microbes. And microbes need carbon for food. We need carbon so even when we say we are eating food, at the primary level, carbohydrates contain carbon as the basic element. It's how you put these elements together to create structures that you have to worry about what happens at the end of life or how does it process. All of those things come into play. Right? So at a fundamental level, we are still talking carbon.
That's great clarification for me personally, and I'm sure other listeners too. Switching a little bit. So what is very interesting for me when I look at a polylactic acid or a polyhydroxyl alkanide is this idea of, in a way, mimicking nature, by microbial multiplication. How do you see that process kind of taking shape in other things? And where I'm coming from is this whole idea that, when you look at modern meadow, they created this whole idea that they're going to take a tissue and synthesize it by artificially multiplying and creating a similar structure as what nature would create from a cow's leather. So how do you see the future of packaging going more and more towards microbial multiplication rather than our subtractive processes that we have in the industry, where we take something, heat beat treat, mush it up, and find and separate it and then create something else. Whereas nature, and in case of PLA, it's more additive manufacturing where it is kind of microbially multiplying. Do you see that to be something that will keep growing and the biological processes will be used more in the future? Or do you think that is just one part of the one direction and it could be multiple directions?
From a economics perspective, I mean, this goes back to my fundamental saying, don't throw the baby with the bathwater out. There is a lot of good with the current polymers we have, right? Which is in the market, the PLAs, the PHAs. Now, the difference between a PLA and a PHA is PLA is produced from lactic acid, which is produced by fermentation, and then you do a chemical polymerization. PHA is a polymer microbially produced. So one is a microbial polyester, the other one is a fermentation polyester. Okay. And companies argue mine is better, that is better. But to me, I think the debate should not be on, at least in this case, what is better. Maybe LCA will tell you that. But the fundamental, what is the end of life associated with this? And does it meet an end of life? So from my perspective, I'm agnostic on what the molecule used. Polymer, it doesn't even have to be polymer. They're all polymers, right? Once you take carbon in the backbone and do it, whether microbes produce it, like you said, microbes multiplying to microbes creating it for us, a microbe factory, for example, which is used, right? Yeast factories to produce high fructose. Yeah, but then economics come into play. I mean, for medical products, they use a lot of microbially produced molecules for drugs and other things because you can afford the cost. So the question is, when we have these molecules available, even from a petrochemical refinery, right? If I'm looking only to the end of life, I should not disregard those kinds of polymers. Otherwise, you're becoming too simplistic. I want it to be all natural. But nature doesn't make, I mean, look at nature itself. I gave you when I last talked about how nature creates biodegradable materials. Let's look at nature's polymers. It makes starch, which is the same glucose unit with a different linkage. It's an alpha linkage. We call it alpha anhydroglucose units. And cellulose, which is a beta linkage. Just a switch in how they are linked together changes it from starch, which is so water dispersible, biodegradable, doesn't, everybody know you cooked rice has got starch in it, to cellulose, which is not that easy to process. That's what gives you paper. So paper is coming from cellulosic materials. Food ingredients is coming from starch materials. But what is the backbone is still a sugar unit, linked differently with different units and all. I'm simplified that. So is cellulose better or is starch better? Well, you need both, of course, right? That's what we are saying. What about lignin? Now, lignin is the glue which holds the cellulose, hemicellulose, and starch. Together, not starch, but cellulose, hemicellulose held together, the bond which holds it. It's got aromatic rings associated with it. Is that usable? Yes. But then you have to process it, right? So you ask that question, Is starch a better feedstock for making PLA, lactic acid, or any of these molecules, biochemicals, or is the lignocellulosic better? And you will find out that in lignocellulosic, you have to remove the lignin, sugar cane. Then you have to find a use for it, which is today burning it. Then you have cellulose and hemicellulose, and they are not the same. You have to separate it to give you your pure cellulosic fiber. And what is the economics associated with it, and what do you do with all of those come into play? That is why even today, ethanol production for fuel additive is never economically competitive if you use lignocellulosic feedstock, because the cost of sugar, let's just very practical term, if you start with 1 kg of lignocellulosic and 1 kg of starch, you will not get the same amount of sugar from both, right? I mean, cellulose will give you the sugar, hemicellulose may or may not, but 30% is lignin. So you're lost 30% by mass of your sugar capacity if you change from starch to lignocellulosic. Why is lignocellulosic better than starch? Because of the perception that that is food. This is thing. But then companies have tried it. They have tried to convert lignocellulosic to ethanol, taken care of the lignin. The technology is there. The economics is not there. It's a very simple math there. You don't have the same quantity generated from both. So why should I not use starch? I mean, there's so much starch available, overuse. If I manage it correctly, this should be there. So there are extraneous discussions which are thrown into it to promote one versus the other. And if you remove all of that, then it becomes pretty clear what should be used, what should not be used. For paper, you need cellulose for sure, right? So you're not going to go and take starch and make paper. So that's
those
how
are the quid
nature
pro
has
quo.
done it. Yeah. So this is why I think the issue which you asked is, are we going to go to these microbial? So there is a product which is where they grow the microbes in the mold and say, look, we can make it. Yes, very unique mycelium is what that is, mold growth, and you can grow it in pots, and they have efficiently made that happen. Compare that to an injection molding process where I can make 1,000 pieces in 10 seconds using a huge processing operation. How will the economics compete? Right? So I think the economics hat needs to be put around all these things, not to discourage and not to move in this direction. We should have these products. Maybe at some point it could become, but it doesn't seem realistic that you would throw away what you have learned, what you have developed, and then say, I'm going to use that. That's not going to work that way. You need to adapt, and you need to utilize plant biomass feedstocks and pump it into the chemical processes which we use today to create products with a defined end of life that has to be proven, not claimed. So just because there is these comments which you see, use of natural polymers, they are automatically assume because it's a natural polymer, it's biodegradable. Right? Lignin will not biodegrade at any rate fast enough. It's actually useful in the compost making, and it doesn't go there. So you can't make such claims. And natural polymers are always safe for use, and nature produces natural toxins which could kill a human being. It's not that all polymers are perfectly. So we make absolute statements which don't make sense except to promote it. But if you look back to it, we need to leverage the best processes we have today, which has been proven economically, and try to substitute different materials that lends itself to end of life in a more appropriate way, including recycle, right? You can design for ease of disassembly, Instead of using multiple layers to make a packaging, can you use mono layers? Can or if you use layers that can be easily um, separated, for all of those comes into play. So the message is end of life must dominate the design of polymers to make that, and that it would be more beneficial to use plant biomass feedstock just because of the carbon cycle, because of agriculture and other things, but not to totally discard any feedstock which is based on fossil, because we have plenty of it. You're not going to shut it down overnight. The driver should be that end of life, which is what we are looking for from a sustainability perspective. And
Super.
that in the process, you don't generate red flags. You don't generate too much of some uh, ingredient or some gas which is problematic, right? That's what we have to
Yeah.
do.
No, superb. I think well put. So switching gears a little bit, and you inferred to this idea of compounding and blending and making multiple materials. You talked about PLA and PHA and esters also in the first kind of carbon chain. So how does this kind of ideation happen that, okay, this is the kind of output that we need in terms of performance, and this is the kind of blend we should create in terms of mixing. And of course, you have the PLA, PHA kind of blend, but we are also seeing a lot of other blends, and it could be PLA, PBAT, or PBS, or something like that. So, talk to us a little bit more, and this is becoming a masterclass. So talk to us a little more about the whole idea of compounding and how that should be looked at.
I think that is the space which is going to give us the most advances. The ability to compound, but to use a much simpler, to mix and match. You have on the shelf a number of different polymer molecules. You mentioned many of them: PLA, PBAT, PBS. The consideration for selection of those molecules is that the polymer at the end of life will still meet all the standards and the requirements for complete biodegradability in a practical time frame. So you have that. Then, based on the applications, you mix and match. That mix and match is done in a compounding operation, which is what they call it's an extrusion operation. Uh, a company like Nature Tech, you're familiar with, that's their focus. They don't make, they're agnostic to what materials are there. As long as those materials, once you compound it, those polymer molecules will still meet an end of life regulation. So, how do you mix it? How do you do chemistries around it? How do you get performance cost ratio benefits out of that? So that's where that part comes into play in terms of this, to make sure that any of those polymer molecules can be used. Each polymer manufacturer is of course going to promote what his product is and what its advantages are. But if we want to learn from the carbon backbone polymer industry, nobody says polyethylene is better than polypropylene is better than poly. All of them have found their applications depending on the application, right? They are there, and they are all equally well used. I think it does a disservice to the nascent bioplastics industry for polymer manufacturers making PHA or PLA or PBAT or PBS to to compete with each other. You first create a market, and then you can compete afterwards. And that's where I think in LinkedIn and other places I see this debate saying PHA is better, PLA is not. Actually, people use both. The real products have both in them, and they use it depending on what the application is. And maybe PHA by itself can also work. And this word PHA is also very misleading, is too strong a word, but it's not correct. PHA belongs to what I call a class of polymers, polyhydroxyalkanoates. And therefore you get PHBV, PHBH, a lot of PHB by itself. So there are different polymers. And therefore, when somebody says, I'm making PHA, what PHA are you really making? And have you evaluated the properties of it? So that's where this lumping up approach doesn't work.
And of course, staying with compounding, when we look at certain properties, like you said, like PLA may have a very good property when it comes to brittleness, but if you want it softer, you kind of blend it with something else. Is that what you're saying? That, it depends on the application and what you need, and that's how the compounding would happen?
Correct. More than just simply is it stiff or is it flexible, it's got to do with oxygen barrier, moisture, all of the other performances you need to give you a good blend of properties that you need. And that's the learning which is uh, happening. But still, cost drives the top selection process. If a PHA today costs $10 a kilogram, you're going to be hard pressed to use it in an application like a planter pot or a pot or that. But if it is for a higher value application, whatever that is, then maybe it is useful to you. So I think cost can and performance properties dictate selection of materials that are compounded, which is the correct terminology, to give you that. And there are several companies which just do that without being specific to one versus the other. So that's really what we're talking about. And that has to grow. So we still need the high volume premium. So when you see these differences being offered in the market as low cost, they're simply switching the amount of the base polymer resins they're using. I use more PBAT because now it's much cheaper than PLA. I use PLA because it's more cheaper than PBAT. So the market economics drives the compounding because of cost.
And if you look at sometimes we get also stuck in this idea of, can it be extruded or dispersed, and that has its own kind of blend of challenges, because we've been working with some people and they say PHA has a huge challenge in dispersion, and then that creates another level of challenge in application, especially if you're trying to coat it. So is there, are there some thoughts there as well on how we can create different applications in terms of conversion process?
What you bring up is sort of the newer development. Paper applications are growing, but it needs a coating, like you said. The the current process for making putting a coat on paper to give you the grease and moisture barrier properties and other oxygen, whatever the properties you need, is extrusion coating. It's a it uses the same fundamental principles of plasticity. You heat it, it flows, and you pull it onto paper, bring it together, and it's done. And it's done. The speeds of that is huge. Uh, the coatings are thin. Cost simply dominates that. So you can produce these paper products at lower price. So the cups and all those things you see. With the realization that people like me saying, hey, you simply calling it paper, but you're hiding the plastic. People are saying, okay, is there another biodegradable polymer coating I can do on it? Will it have to be extrusion coated? So the coatings process can be divided into one is extrusion, which is simply melt and uh, put the film on it, or you use a solvent. And the solvent process lends itself to coatings which are from a manufacturing applies to low cost manufacturers. It gives more opportunities for more small companies to get in and do coatings, the gravier coating and things like that. Those types of technologies apply. So that is when they talk about dispersions and water. I'm sorry, solvent borne. But solvent means you have another volatile organics problem and you have to deal with. So the coatings industry says, I want a waterborne emulsion or a waterborne coating. Okay. Which means how do I disperse a PLA or a PHA in water and stabilize it, right? You can disperse it, but it will settle down. So how do you stabilize it? And there's a whole technology around it, uh, which I think is where the paper industry and your industry, and especially if you look at it, is going to have to look at to review, right? So I think that with the polymers of today, the ester backbone, the ones which lend themselves to biodegradability, although you still maintain that you have to prove it, but is much more amenable to biodegradability than carbon-carbon backbone, then solutions coatings will work. And for that to be really commercializable, if you're looking at it purely from an environmental perspective, you need water-based dispersions. Then you are totally eliminated. Oh, you're using solvent, you have problems with solvent. Can solvents be a stepping stone to waterborne? I That is a question which we can ask. Are there solvents which you can use which would lend itself to it? That's also a good question uh, to be asked. But today, uh, for example, PLA, what is its solubility in ethyl acetate is a solvent used. I'm giving you all the trade secrets here. PLA, ethyl acetate, good solvent. Can we use it? That's where the economics, that's where the environmental regulations come into play. But there are PLA molecules which are now being created, which can lend itself to that kind of application. Uh, More biodegradable. Remember, PLA has got a window where you need to be at industrial composting conditions to make it biodegrade quickly, rapidly. But can you change the PLA molecule so that you can do this? That's work is also intriguing and it's happening in the world. And can I make a water dispersion? Those are challenges today. It's not commercial, but I think we will move more. I think the ultimate holy grail is extrusion coating because that is a proven technology. Uh, if you can make thin films like polyethylene, that is your gold standard. Can I take a polymer which is fully biodegradable, certified, and process it in a machinery which uses polyethylene today at the same rate, at the same thickness, then you have a winner, which probably will not work, which will not happen because the process has been so fine tuned for polyethylene that may be difficult, but still, it is a holy grail to go after.
It's good for me to know because as a paper maker, we always think of dispersion as more of the holy grail because we can do it at speed at our mills with, long, with much thinner kind of water-based aqueous kind of coating solutions running at 1,000 meters per minute. But it's always this debate, because you're right. Extrusion coating happens all over the place. Smaller extruders can do it, and it becomes a more generic process rather than
Yeah,
a large kind of coater with with much stronger metering needs to kind of be able to
yeah.
coat. So okay, all great conversations have to have a arc, and we have to go towards the end because I've taken 2 slots from you now. One of the key questions, and this is where your mastery again lies in amongst many other ideas, and this is a huge debate that continues, right? Home composting, industrial composting. So, so of course we understand that industrial composting is in controlled conditions, it's at scale, whereas home composting is something that might degrade in the open kind of if it's just strewn in wherever there is microbial activity, and it may not be temperature controlled. But it's obviously not as simple as that, right? So I remember the first time I met you, we talked about this idea, and what we have noticed, at least in our case of using a lot of PLA, that in a temperature like India, it actually literally starts composting on the shelf at some point. So, and Sundar and I have had numerous back and forths on that. How do we solve this? And vice versa, there are certain things like even our containers. Once we add OGR chemistry to it, sir, it's difficult to home compost. And it is difficult to break down even in a composter at times. So at least from your perspective, if you can again dumb it down for us and say that, okay, this is how it really works and this is what it means in terms of both those terms.
I'm not a fan of designing products for home composting because can you control what happens in every home in the country? Leave alone, how they do what they do. Forget temperature, forget everything. So that is an issue in itself. That home compostable is a kind of to use a generic phrase, cop out. You dump it on that. You don't have to build the infrastructures and all. So I am home compostable. So I because home composting has got so many different facets to it, it seems to suggest that home composting is somehow different from industrial composting. That's what we have come down to. And my pushback, and I'm probably on the minority here, composting is well known, well defined. You don't add an adjective like a home composting and says, well, people at home don't follow the root product protocol and temperatures don't go up and here is the problem. They're doing it wrong. Why is that acceptable? Not to say they shouldn't do it, but the key differential, which in the standards and everything says, you correct me, is that's where your temperature thing comes into play, is the home composter setup may not give you high temperatures of industrial composting and period of time. The industrial composting is a managed process. So let's separate the two. Home composting is what you do, no controls, no regulations, and then a homeowner is going to come and say, yeah, you told me this is home compostable. It did not. There is a study which was done in the UK. I don't know if you know, and there's another study which was also done in Germany where they took certified home compostable products and gave it to, I think, 100 households. This is a published study. They call it citizen science. And found out that in 50% of the cases, the certified home compostable did not work. That was a headline. But what they did not say that in 50% of the cases, it did work in home composting because they did it correctly. But the headline was home composting doesn't work with certified products, right? So that's what you're getting into. So I would urge everybody to stay away from this home composting, the terminology and saying that I can make a product which will So what you're basically saying is, I will make a product which will biodegrade in your home disposal system, no matter what you do. If you make a product, you put conditions, right? You got to use it. You can't take, even today we say, a plastic bag. You put a condition that don't put it on babies because of this happen. So that is where this home composting thing is. I wish we stay away from home composting as a goal because you can never achieve it. The second part to that is composting is a managed process. That's where the word industrial comes, which leverages both the mesophilic temperatures and thermophilic temperatures and cure in a continuum. It's a process. You can't mismanage that and expect things to work. And I want to leave you with what composting is because I think that will answer it. When you feed microbes a substrate, food substrate, right? The microbes start to recognize that carbon, secrete enzymes, whatever, and starts to utilize it. When microbes starts to utilize carbon, Those microbes are called mesophiles. They operate at room temperature. They start to consume the microbe. That is um, a process which generates heat. It's an exothermic process. The process of mesophiles consuming carbon is a exothermic process which generates heat. The temperature of the pile goes up. When it reaches a certain temperature, mesophiles go dormant. The thermophiles in that pile start to operate and break down faster, quicker, and better. So it's a continuum of mesophilic, thermophilic. And when all the carbon is used up, there's no more carbon available, the temperatures start to drop. And then you let the cure process take place. That is a chemical process over a period of time to take place. That is composting. Now we have totally messed this up to claim I can just simply throw it in my home. Yeah, it works, but you never know what it is and how it is, right? So I think that this is also saying that I don't need to build industrial composting managed processes because I want to make a package which goes in. And my fundamental pushback to everybody is you are going to need managed composting processes to handle 50 to 60% of biodegradable organic waste, including food waste, which is there. And that takes this process. And if you don't do it correctly, then you're going to cause problems. You can't take food waste and dump it. Even in home composting, you are careful what you put into that. So we need to be very careful in going down this home composting route and allowing every individual to become a waste management expert at their homes. That is going totally off. We need to have managed processes, which it could be decentralized, it could be in closed locations, but it has to be done right. Otherwise, you're going to create another whole set of problems over there. So that is about home composting. That doesn't mean you shouldn't have soil biodegradability like mulch films and all, where it is more controlled. We know what time frames you are looking at, we know what temperatures we are looking at, and then you have standards for that. So that is where I think a big problem exists in the composting field, because many countries are saying it needs to be home compostable. And I'm saying you cannot meet home compostable because the standard test, there is a standard in EU and now even in this, which tests for home compostable. You know what the test is? They simply bring the temperature down to 25 degrees, but follow the same protocol. So what are they doing? They're simply not allowing thermophilic microorganisms to operate, but they're simply allowing only mesophilic organisms to operate. So it's not really composting they're doing. They're doing soil biodegradability type tests, or they're doing mesophilic composting, quote unquote. That's not composting. Running it at mesophiles is not composting. And that is where the problem is. But
Super
this is a
interesting. Thank you.
minority position
Yeah.
on
No,
this. More people need to get educated on that.
no, and thank you for explaining it so well. Even I'm kind of I'm more aware of the ideas around that, and of course, it'll make my daughter especially happy because I have like 6 types of composting devices, and they're electrical, and the tumblers, and the bokashi process, and all of that. And I love the smell, and she hates it, right? So I'm like, go take the compost away. She's like, Dad, I don't want to do it. So so I hope she doesn't hear this conversation because she'll be like, see, I told you, you should just put it on the industrial compost, guys, and let them do it rather than you trying to do all this kind of drama around composting. So
No,
okay,
but
like
composting is correct, Wade, because for your kids and all, you use defined ways for you to do it. Certain which is approved and you know what you're doing, right? But don't expect it to be a magical solution for handling the waste. That's where it comes to.
yeah, no, absolutely. And that said, all home compostable products would definitely compost on an industrial site too. But I like your
Absolutely.
idea. Just call it compostable. You don't have to make it home and industrial and all that. And they can all be taken to a structured composting system And of course, they will all compost. Then it doesn't need industrial composting is anyways good for home compostable products as well. All right,
yeah,
final two. What is really important for the world of packaging to shift is scale. So, we're talking about billions of tons of materials. So, when you look at especially polylactic acid, we see a lot of plants coming up. There's one in India, 75,000 ton capacity. Thailand has gone to 150,000 tons. India is also talking about, Balrampur Chini talks about, okay, as soon as this is done, we'll put in another 75,000. So, if you were to look at a crystal ball and have your aspirations high, what would you say should be an ideal capacity that the world should have in the next 5 to 10 years?
let's frame it with the plastics production, right? 400 million metric tons plastics production. Today, we are not even at maybe 1% of that. If these end of life becomes more apparent, then we should be at uh, 10 to 20% in the next 5 years, which is a pretty ambitious target. So that means you're saying uh, if 400 million, if you are at 10, it is 40 million metric tons. And even if you're at 20, that is 80, that would be a stretch goal to achieve, right? Now, if you say 40 million metric tons, your PLA capacity, which you have said, doesn't meet that. So you're going to need a lot more. You're going to need uh, other kinds of PHAs and polyesters to get to that 10 to 20%. That's why I said we are unnecessarily arguing about is PHA or PLA or PBAT. You're going to need that if you're going to create that level of entry into this marketplace, right? Otherwise, we'll always be a niche player, fighting for the crumbs and not really make an impact environmentally or from a market perspective.
And probably it includes the newer materials, like we're talking all about alginates and things like that
Yeah.
are coming in as well. So hopefully they will create a dent as well. Okay, my final question, and I'm very excited to hear your version of this. What does good garbage mean to you?
It's a very intriguing word, is all I could say. To me, good garbage would mean that you're treating it correctly. You have, as a person, but even as a country, as a policy, you are diverting it to end of life management systems, whether it is composting, whether it is recycling, to ensure that that doesn't leak into the environment, right? And cause problems. So good garbage is bad if it is simply thrown out and leaked into the environment to cause impacts. Garbage is good if you can manage it and utilize it. It's great if you can create some value out of it, but certainly you need to manage it in an environmentally responsible manner. So that is good garbage. So I think it's an it's an elegant choice of words. That there is garbage which can be good, and there is garbage which can be bad, and the same good garbage can be bad garbage if you don't manage it properly.
Thank you so much.
So
It is such a joy to interact with you each time. And I'm always amazed at your generosity of, I know you're a very busy person, but your generosity of time, like I keep troubling you that, this is not a 3:30 a.m. conversation. So I know that you've woken up at 3:30 a.m. to join conversations, and the passion that you bring into each of these discussions. I could have gone on for another 4 hours. I had enough questions that I didn't get into because of paucity of time in the end. And of course, being respectful for your time. And also, the other thing, Dr. Narayan, is always the free sharing of knowledge. Each time I speak to you, I'm definitely a more educated person. Like, there are 10 more things that I've learned. So thank you for being the person you are and the amount of influence that you've had in so many lives of people like me and many others who are actually doing things because of the impact that you've had in our thinking. So thank you so much for being the person you are. Thank you for your time, and thank you for your patience with me.
thank you very much, Ved. I enjoyed the conversation. So, and more power to you to continue in that direction.